So we will continue our discussion on non-inverting amplifier. So we have seen non-inverting amplifier, okay, and this is the circuit that we have seen. This is plus, and here the voltage is V in, okay, and this is V out. There is a feedback through the resistance RF, and this resistance we will call it as Ri, or I can draw the same circuit in another way. This is minus, this is plus, okay, this is V in, okay, both are same anyway. So this is V out, okay, and this is RF, and this is Ri, and okay, so Ri, and I can connect like this, both are same. Okay, now I told you about the feedback voltage, which is Vf, and this voltage I told you this is Vd, and this voltage is V in. Here it is V in, so this is also V in, and this voltage is Vf, so this is also Vf. Okay, both will be same. Now what is Vd? What is Vd? I told you about Vd is equal to V in minus Vf, and I told you because of the virtual short, your Vd and virtual short is because of the high gain of the op amp. Okay, it is because of the high gain of the op amp. So due to the high gain of the op amp, I told you that is Vd is approximately equal to 0. That means your V in is approximately equal to Vf. Okay, so that is the advantage, and we have seen that. So this is V in, I told you about this is V in, and this is Vf. So V in is approximately equal to Vf, and also I told you about the feedback factor B is equal to Ri divided by Rf plus Ri. And what is the voltage gain? If you know the open loop gain, what is the closed loop gain? It is equal to, if you know the open loop gain, the closed loop gain will be equal to, closed loop gain is equal to AOL divided by 1 plus B into AOL, which is equal to 1 by B, right? And it is nothing but 1 plus Rf by Ri. So this is the closed loop gain. This we have seen all this analysis. Now we will see one problem based on this. You can see one problem here. There is an amplifier. You can see that the input V in is connected to the positive. So which kind of amplifier this is? So I am going to write the answer. This is a non-inverting amplifier. Okay, basically it is a non-inverting amplifier because the input is connected to the positive terminal. That's why. Now I told you, if so, what is the procedure? We will look at the positive terminal, and this voltage I told you this is V in. So this is nothing but your Vf, but your Vf will be approximately equal to V in, and the reason for this I have already explained to you. So this voltage is V in, so this is approximately equal to V in. Now we will write the Kirchhoff law at this node. Let's say this is I1, this is I2, this is I3. You see here that I have assumed all the currents are leaving from the junction. This assumption has no issue, because if your assumption is wrong, you will be getting a current which is negative. That means that if you are getting a current as, suppose if you are getting a current as a negative value, that means that the actual current is in opposite to the direction that you have assumed. So I told you, so we will apply the KCL here. So apply the Kirchhoff current law, okay, and the voltage is V in. So I told you, what about I1? That means I1 plus I2 plus I3 is equal to 0. Since the currents are leaving from the junction, you have to consider this voltage first. Okay, first you have to consider this voltage. Okay, so I1, but I1 is flowing into the op amp, but into the op amp there is no current because of the high input impedance of the op amp, so you can assume that the current is approximately 0. Okay, but actually there will be some very small current, but we can assume in the circuit analysis for simplicity that it is approximately 0. So this is 0 ampere plus I2. What is I2? I2 is this current which is going into the ground. So it is nothing but V in minus this voltage. I told you this is ground, so it's 0 volt. So 0 volt divided by Ri, right, plus now I3 is the current which is going to the top. That means it is nothing but V in minus V out divided by Rf, right, and this total will be equal to 0. Now we can see that means now we can write it as V in by Ri plus V in by Rf minus V out by Rf is equal to 0. This means that V in, I can take this V in common, 1 by Ri plus 1 by Rf is equal to V out by Rf, right? Now I need V out by V in. So V out by V in is equal to, you see here, I can move this guy here and I can move this guy onto the top. Okay, that means that Rf into 1 by Ri plus 1 by Rf, right? So you will get it as 1 plus, this is Ri, okay, sorry, Ri, not Ri or Rf. Yes, it is Rf, sorry, it's Rf. So it's become 1 plus, so because if you multiply this, you will get Rf by Ri plus Rf by Rf, right? Now V out by V in, you can say this is nothing but your closed loop gain, which is equal to this term become 1. So 1 plus this term will be Rf by Ri, right? So this is the closed loop gain. So it's very easy to calculate. You don't need to remember the formula, but I recommend you to remember this formula at least for 2 amplifiers. Okay, and now what is the gain? We will see. We know that our Rf is, for our example, our Rf was let me see what is Rf. Rf is 100 kilo ohms, and Ri is 4.7 kilo ohm. So I can easily calculate my gain. Okay, I can easily calculate my gain using this 1 plus 100 kilo divided by 4.7 kilo ohm. Okay, so this is the answer. I hope this is clear to you. Now let me check what is the value for this calculation. So the answer is 22.3. Okay, so this is the gain of this particular op amp. Now we will see another op amp, which is another op amp configuration, which is known as the inverting amplifier. So the procedure is almost the same. So we will see what is inverting amplifier. Okay, so the procedure is almost the same as that of the non-inverting amplifier. Okay, we will see what is inverting amplifier. So inverting amplifier. So what is this? If you give the positive input, the output will be just opposite x of the input. That means the negative sign you will get. If you give the negative voltage, you will get the positive at the output. Okay, this is the beauty. Now we will see the circuit diagram for this. So inverting amplifier, this is plus and minus. There will be feedback, definitely. I told you we need a negative feedback for controlling the gain of the op amp. Otherwise the op amp will get saturated. Okay, now this is V in. Okay, that's it. This is the inverting amplifier. You can see here that the input is V in, and it is given to the negative terminal. It is given to the negative terminal. That's why if you give the positive input, you will get the negative output like this. Okay, negative. If you give the negative input, you will get the positive output. Okay, now this is your V out. Okay, it's your V out. Now I told you that this is directly connected to the ground, so we will do the circuit analysis. Now this is 0 volt, so this is also 0 volt. Okay, this is also 0 volt. Now what will be the voltage here? Let's say this is VA, some voltage is VA, this is some voltage VA. Now I told you the current going into the op amp, let's say this current is I2, which is equal to 0 ampere, because current going into the op amp is 0 ampere. I can apply the KVL in two different ways. Okay, engineer Abdurrahim will be teaching you maybe one way. I will give you two ways, both are same anyway. So this current, let's assume that I1, and this current I assume that I3. That means I assume that all currents are leaving from the junction. If my assumption is wrong, I will be getting a negative current. There is no issue. Okay, so I can assume like anything. So I assume that all the currents are leaving from the junction. Now if I apply the KCL, it becomes I1 plus I2 plus I3 is equal to 0. But I told you I1 is equal to VA, because that voltage we have no idea. So I assume that it is VA minus V in divided by, let's say this is RI. Okay, RI, right? And I2, what is I2? I2 is equal to 0. And what is I3? VA minus V out divided by RF, right? VA minus V out by RF. Now I am going to write the Kirchhoff law here. Okay, so VA minus V in by RI plus 0 plus VA minus V out divided by RF. This total is equal to 0. That means VA by RI plus VA by RF, okay, minus V in by RI is equal to V out by RF. Is it clear? Because I am just rewriting the equation by keeping some terms on the left side and some terms on the right side. So this is nothing but VA into 1 by RI plus 1 by RF, 1 by RI plus 1 by RF plus, sorry, not plus, it's minus. So minus V in by RF is equal to V out, okay, divided by V in by RI, right? Sorry, V in by RI is equal to V out by RF. So I hope this is clear. I will redraw the circuit again for your convenience. Minus, this is plus. I will redraw the circuit. Same thing, RI, and this is your RF, and this is your V out, and this is your V in. Okay, and we have this voltage as VA, and I told you this is 0 volt, so this voltage is 0 volt. Okay, now let us assume I will give you an assumption. Okay, let us assume that this is VD. Okay, what is VD? So what is my output? My output will be equal to the open loop gain of the op amp multiplied with VD, right? This will be my output. And what is my VD? My VD is nothing but this is plus, so 0, and this is minus here, so 0 minus VA, right? That means 0 minus VA, that is my VD, right? So AOL into 0 minus VA is equal to V out, right? Let us assume that my output was 1 volt. Suppose V out equal to 1 volt. Okay, V out is equal to 1 volt, and the gain of the op amp was 10 power 6. Then my VD, in such case, what is my VD? This is my VD, or I can say this is VD. So what is VD? VD is equal to V out divided by AOL, right? It's 1 volt divided by AOL will be 10 power 6. So it is 10 power minus 6, which is nothing but 1 microvolt. That means that my VD is equal to 1 microvolt. That means my VA, what is my VA? That means my VA, I can write from this equation, VD is equal to 1 microvolt is equal to minus VA. That means this is very small number. I can say that this is approximately equal to 0. That means my VA is approximately equal to 0. That means my VA is approximately equal to 0. That means you see here, when this voltage is 0, my VA is also approximately 0. This is due to the high gain of the op amp and the feedback. Okay, so what I am saying is here, my VA is approximately equal to 0 because of the virtual short. Because of the virtual short. So this virtual short, you see here that this is minus, this is plus, and it is here right like this. Okay, I will draw the circuit again. This is my RI, this is my RF. So V in, so I told you this is 0 volt, so this is also 0 volt, and you know that the 0 volt means it is the ground voltage. So this voltage is also 0 volt, means that this is also at ground, but actually it is not connected to the ground. But we can say that it is not in a true sense, but in another sense. That means it will follow the same voltage of the non-inverting terminal, or we can say that they are virtually short, or they are virtual grounds. So this is the concept of virtual ground in op amp. This is very important concept in analyzing the circuits in electronic circuits. Okay, analyzing the electronic circuits. So this is your V out. So what is the idea? Look at the non-inverting terminal and identify the voltage, and identify the voltage. Now here that voltage is 0 volt. So at inverting terminal, the voltage is also 0 volt. And this concept here in this non-inverting, sorry, in the inverting amplifier, that means this is IA means inverting amplifier. So this is the case in the inverting amplifier, and this concept here, it is known as the virtual ground. Okay, virtual ground. Now it's very easy. You had the equation, this one, let's say this equation is 1. Okay, you have the equation, it's VA into 1 by RI, 1 by RI plus 1 by RF is equal to, sorry, not equal to, minus V in by Ri, right, is equal to V out by Rf, right? But you know that my VA, this guy VA is equal to 0, approximately equal to 0 actually. So it's equal to 0. So this whole term will cancel. So I will get my V in by Ri is equal to V out by Rf. But I want the gain, closed loop gain, as V out divided by V in, which is equal to minus Rf by Ri. How? You can move this guy here and you can move this here. So you will get V out by V in. So you see here, this is the gain of the op amp. So for the inverting amplifier, right? For the inverting amplifier, this is the gain. So we will see a problem now. Okay, we will see a problem. We will see an example. You see here, this is minus, this is plus. Now this is 1 millivolt. Okay, this is 1 millivolt, and this is 1 kilo, and this is 10 kilo ohm. Okay, this is your Rf and this is your Ri. Now you are applying a V in, which is 1 millivolt, and this is V out, and you want to find what is V out. Find V out. So first of all, we have to, for answering this question, we need to write the equation for V out. What is V out? V out is equal to the closed loop gain, because this is a closed loop circuit, into V in, right? But what is closed loop gain? So don't write the equation as such. Okay, we know from the previous proof that it is Rf by Ri, minus Rf by Ri. You can see a minus sign because it is an inverting amplifier. It will change the sign, that's why. Now I will write the Kirchhoff laws. So this is 0 volt, so this is also 0 volt according to the virtual ground. Why? Because of the virtual ground concept. Okay, virtual ground concept. Now you can apply the Kirchhoff law here. Let's say this current is I1, this current is I2, and this current is I3. So I1 plus I2 plus I3 is equal to 0. Then it's become 0 minus V in divided by Ri plus 0 plus 0 minus V out divided by Rf, right? This is equal to 0. If you solve this equation, you will get V out by V in is equal to minus Rf by Ri. So this is the proof. Anyway, within one step you are getting the proof. So what is my output? What is my closed loop gain? It is minus Rf by Ri. Okay, I will write with another color. Minus Rf by Ri into V in, right? This is equal to minus, okay, 10 kilo divided by 1 kilo ohm into, what is my V in? My V in is 1 millivolt. So this is nothing but minus 10 into 1 millivolt, which is equal to minus 10 millivolt. This is my output. So what is my gain? My gain is, this is my gain. My gain in the closed loop, that is equal to ACL, which is equal to minus 10. That's what. This is my gain. So I hope this problem is very clear to you. So we have two op amps now. Okay, I am summarizing. Summary. So first op amp is a non-inverting, op amp circuit is a non-inverting amplifier. What is that? Minus plus, okay, and this is plus and this is minus. Okay, or I can write in another way, that's better. You see, this is minus plus and this is my V in, okay, and this is Rf and this is V out, and this is my R in, and this is ground. So this is non-inverting amplifier. Now it's inverting amplifier. So minus plus, okay, that's it, this is RF, this is RI, but I will give the input to the minus terminal. That's why it's known as the inverting amplifier. Okay, inverting amplifier. Now this is grounded. Okay, now I told you about the voltages. This voltage is V in, so this voltage also will be V in. Now here on the inverting side, this is 0 volt, this is also 0 volt. So you have to first look here, look here, right? So then see what is the voltage. You can assign the same voltage here. Here it will be same. Okay, you can see here it will be same. Then you can apply the Kirchhoff laws. Let's say this current is I1, this current is I2, and this current is I3. Same like here also. This is I1, this is I2, and this is I3. You see here I2 will be 0 anyway. Here also I2 will be equal to 0 because it is going into the op-amp. Because of the high input impedance of the op-amp, you will get it as 0. Now, what is the gain? The closed loop gain is equal to, this is a non-inverting amplifier, it is 1 plus RF by RI, and this is closed loop gain is minus RF by RI. So these are all the two circuits. So you should remember this. Okay, you should remember this. Okay, now we will see one problem. This is a problem. An op-amp has been given, and you see here that the input is given here, and this terminal is negative. So this is an inverting amplifier. Okay, and what is the gain of this amplifier? The gain of this amplifier in closed loop is nothing but the closed loop gain is minus RF by RI. Now has been given that the gain is given. So what is the gain? The gain is given, and it has been given that the gain is equal to minus 100, and RI is also given. You see here RI is given, it is 2.2 kilo ohm. So what is my RF? So RF, that is the question. So this is the question. So I know that minus RF by RI is equal to minus 100. That means my RF is equal to 100 times RI, which is 100 times 2.2 kilo, right? So that is the gain of this particular amplifier. So this is a very simple problem anyway. So I hope this is clear to you. Now we will see another circuit which is very important in circuit theory, which is known as the voltage follower. Voltage follower is a circuit with the unity gain. We will see how to set the gain as 1. So this is the circuit, minus, plus. Okay, that's it. Now I am feeding back without any resistance. I am feeding back all the voltages. Now this is V in, this is V in. Okay, now this is V out. Can you tell me what is the output? It's very simple. I told you your VD is approximately, in any case, your VD is approximately 0. If VD is approximately 0, this voltage minus, let's say this is V minus and this is V plus. So you know that V plus is nothing but the same voltage as that of V in, but V minus, what will be my V minus? V minus, you see, it is the same voltage from the output. You see here, this is the output and it is connected like this. So it is the same voltage of the output, and my VD is nothing but the voltage at the positive terminal minus voltage at the negative terminal. This is nothing but equal to 0. So 0 is equal to V plus is V in minus VD, sorry, not VD, V in minus V out, right? That means V out will be equal to V in. That means if you give here 1 volt at the input, you will get 1 volt at the output. If you give 2 volt at the input, you will get 2 volt at the output. So what is the advantage of this voltage follower? you may have a doubt that what is the advantage of this voltage. This is used for mainly for impedance matching. This is the main application, is the impedance matching. Okay, because this is an op amp. This op amp has high input impedance and low output impedance. See here, it's low output impedance. Okay, so what is here the gain? The closed loop gain is equal to V out by V in. So this is nothing but 1. So the voltage follower has the gain, actually basically it is equal to 1. The closed loop gain, okay, closed loop gain is equal to 1, or just voltage follower has the gain equal to 1. So what is the main advantage of this? Because it has high input impedance and it has low output impedance, it can be used for impedance matching. I think you know what is the advantage of high input impedance and low output impedance. Okay, now it is for if you want to connect a small sensor which is producing a voltage of the order of millivolts, you can first connect the voltage follower. After that you can connect whatever circuit you like. Okay, so it will not change the voltage output from the sensor, but it will capture everything. But if you connect some other circuit directly, it cannot capture complete voltage. Okay, there will be some loss because of the impedance mismatch, resistance mismatch. Okay, so that is the advantage of the voltage follower here. Now we will see why it is important. I will give you a brief explanation. Suppose you have a sensor which is producing some voltage, let's say voltage at the sensor. Okay, now this sensor has some internal resistance Rs, and this is your op amp. This is your op amp which has the input resistance which is almost infinity, let's say. Then what will be the voltage at this point? This voltage, let's say it's Vb, this voltage will be equal to Vs divided by Rs plus infinity into infinity, or infinity means it's like an open circuit, you can say open circuit, or I can say this is not infinity, it's very high, Zin. Okay, so it's nothing but Vs divided by Rs plus Zin into Zin. If Zin is very high, then Vb is approximately equal to Vs. That's advantage. Okay, if Zin is very low, then Vb will be very small. So if we want to transfer the maximum or the voltages to make available at the input side, we have to use this kind of voltage follower. So this is used for the voltage follower. Voltage follower is used for the voltage follower. Sorry, I have written here. Voltage follower. Okay, not follower. Follower. The voltage follower has the important advantage that it has high input impedance. High input impedance. Okay, this is the highlight of this. And the gain is closed loop gain, that will not change the voltage at all. It's approximately 1. Okay, so that is the advantage of voltage follower. I hope you understood what is the idea. Now we will see the effects of feedback. We will see some more about, we have just seen the effects of feedback on the gain of the amplifier. Now we will see the effects of feedback on impedances. So first of all, we will be considering the non-inverting amplifier. So we will consider the non-inverting amplifier. After that, we will consider the inverting amplifier. You know that the non-inverting amplifier, you have, I can draw like this also. Okay, that's it. Here resistance, this is Rf, this is Ri, I told you this one, and this is V in. Now this voltage is Vd. Okay, now I can say that my voltage, this is Vf, so this is Vf. So what is my Vd? Vd is nothing but V in minus Vf. Okay, so what is my V in? V in is equal to Vd plus Vf. I am writing this equation first. Okay, now what is my input impedance? I told you for the op amp, basically there is some input impedance here, and this input impedance is Zin. But what will happen if you connect the whole thing in a closed loop? If you take a single op amp, it also has Zin, but after connecting it to the feedback, what will happen? So you are standing here and to observe, that means you are observing from this side. If you observe from this side, you can measure what is the current going inside. So what is my Zin or Rin? You can say Zin for the non-inverting amplifier is nothing but you have applied a voltage V in and you are getting a current I in. That means Zin by definition is nothing but V in by I in. But you know that from the equation for Vd, V in is equal to Vd plus Vf, and we know that what is Vd, what is Vf. Okay, this is Vd plus what is Vf? Vf is equal to beta times V out. What is beta? So this is V in, and beta is equal to Ri by Rf plus Ri. We have seen this many times. Okay, so this is my V in. Now you see here that what is my yeah, okay, now this is my okay V out. Okay, V in is equal to Vd plus beta times V out. Okay, now what is my V out? But my V out is nothing but, you know that this is V out, and you know V D, and you know what is the open loop gain of this. So V out is equal to Vd into AOL, right? So I have got another equation for V out. Now I will use these two equations and write something. V in from the equation 1 and 2, I will rewrite equation number 1 as V in is equal to Vd plus B times, what is my V out? It is nothing but Vd times AOL. So this is nothing but 1 plus B into AOL into Vd. But my Vd I can write in another way. You know there is an impedance here, and it is the Vd is nothing but the voltage across this resistance. Okay, so my Vd I can write it as the current is going inside. So I in, it's very small current anyway, I in into Z in. Okay, so I can write my Vd as 1 plus B here into AOL into Vd is nothing but I in into Z in. Okay, now this is my V in. So I got the equation, very important equation. Okay, I will write here itself. So I will write here my V in divided by I in. From this equation I will rewrite is equal to 1 plus B into AOL and into Z in. So what is this Z in? This Z in was in open loop. So this is nothing but V in by I in is nothing but our Z in for the non-inverting amplifier. So this is nothing but our Z in non-inverting amplifier, which is equal to 1 plus B into AOL into Z in, and this is for the open loop. So you see here that the open loop response is multiplied with 1 plus beta times or B times AOL. That means Z in non-inverting is nothing but 1 plus B into AOL into Z in. This is in the open loop and this is in the closed loop for non-inverting amplifier. That means that your output, sorry, not output, the input impedance increases with closed loop, right? Closed loop. That is the main point that you have to notice. So you are getting a good condition actually. Basically you want high input impedance for any amplifier. So by feedback you are getting it. Okay, now we will see another property, output impedance. Output impedance. What about output impedance? Actually I am not going for the proof. You can see that Z out non-inverting will become Z out divided by 1 plus AOL into beta. That means Z out output impedance decreases with the feedback. This is what our condition which we need. It's a good condition. Both are good. This is also good. This is also good. That means the output impedance decreases. That means decreases. I will note output impedance decreases with feedback. Okay, output impedance will be decrease with the feedback. So this is the advantage of the feedback in inverting. This is non-inverting amplifier. So we will see a problem based on this. So what will be, can you tell me what will be for the voltage follower, what will be the, this is the voltage follower. I told you output voltage will be equal to input voltage. Now what will be the value of B here? What will be the value of B here? What will be the value of B here? The value of B will be equal to, I told you that in the voltage follower, in case of voltage follower, this is minus, this is plus, this is your V in, this is V out. What is B? B is nothing but RF by RI, sorry, B is equal to Ri divided by Rf plus Ri. And what is my feedback voltage? Feedback voltage is usually written, if there is Rf and Ri, my feedback voltage is usually written as what? My feedback voltage is usually written like this, right? It is nothing but B times V out. But here my, so here there is no Ri, there is no Ri, and there is no Rf. Okay, there is no Rf. But my Vf, I told you my Vf is equal to V in, and my Vn is equal to V out. That means that my Vf is equal to V out, right? That means my B is equal to 1. So for voltage follower, my B is equal to 1. Okay, B is equal to 1. Now we will discuss about the input impedance of the voltage follower. So what will be the input impedance of the voltage follower? Z in non-inverting configuration. This is a non-inverting configuration. It is 1 plus AOL into B into Z in. But my B is equal to 1. That means that it is 1 plus AOL into Z in. This is my Z non-inverting. Okay. This is for the voltage follower. For the voltage follower. Z in for the voltage follower VF. Okay. Voltage follower, I will just write it as VF. So this is my voltage follower. Now what will be my Z out for the voltage follower? It will be Z out for the open loop divided by 1 plus AOL. That's it. So it's very simple. Okay, just put b equal to 1 in the previous equations. Okay, now we will see a problem. Determine the input and output impedances of amplifier given below. Okay, it is given that the Zin is equal to 2 mega ohm. This is in open loop. Okay, open loop, and Z out in open loop it is given as 75 ohms, and AOL is equal to 200,000. It's very high. Now we want to find the input impedance, output impedance, and one more point I will add, the closed loop gain. Okay, that's it. Now the amplifier is like this, plus minus V in, and this is RF, this is RI. Okay, now regarding the first point, input impedance, I am going to write the answers. Input impedance is nothing but Zin. This is a non-inverting amplifier, which is equal to 1 plus AOL into B into Zin. And what is my B? That's what I want to calculate first. So this is given as 220 kilo ohm, and this is given as 10 kilo ohm. So what is my B? My B will be equal to 10 kilo ohm divided by 220 kilo ohm plus 10 kilo ohm. So I will get this number as 0.0435. Okay, this is my B. So I can calculate 1 plus, what is my AOL, 200,000 into B is 0.0435, and Zin is 2 mega ohm. Okay, so I will get this number as 17.4 giga ohm. You see, it's very high input impedance. Okay, we are getting like this. Now Z out, I can calculate my Z out as Z out non-inverting will be Z out divided by 1 plus AOL into B, which is nothing but 75 divided by 1 plus AOL is 200,000 into B. What is B? 0.0435. Okay, that's it. So I am getting 8.6 milli ohm. It's beautiful number actually. It's very small. Okay, that's it. So I got this answer and this one. Okay, now what will be the closed loop gain of this amplifier? The closed loop gain, I am going to write the closed loop gain, ACL, is nothing but 1 plus RF by RI. So it's nothing but 1 plus 220 kilo ohm divided by 10 kilo ohm. So it is 23. The voltage gain is 23. Okay, now we will see one more problem. For this. So this is question number 1 and 2. So another problem. Determine the Zin for the voltage follower and Z out for the voltage follower with the open loop gain as 200,000 and Zin in open loop is equal to 2 mega ohm, and Z out in open loop it was 75 ohms. So for writing this answer, we know it is a voltage follower. Determine for voltage follower. Okay, voltage follower. Since it is a voltage follower, we have B equal to 1. So Z in voltage follower is equal to Zin is equal to 1 plus AOL into B and there is no b here, b equal to 1 here basically, into Z in. Okay, you will get this answer as 1 plus 200,000, okay, into 2 mega, which is equal to 400 giga ohm. It's very high, it's almost infinity, you can say, like infinity. Okay, and Z out, voltage follower, is equal to Z out divided by 1 plus AOL, which is equal to 75 divided by 1 plus 200,000, which is equal to 375 micro ohm. It's almost zero. It's very high for input impedance and very low for output impedance. This is what the condition that we need. Now we will see, I hope this is clear to you. We will see one more thing. After that we will wind up this lecture. So the impedances, another topic, impedances of inverting amplifiers. So we have seen for non-inverting case. So we will see first the see first the inverting amplifier. So this is inverting amplifier Ri, and this is RF, and this part is grounded, and this is your V in, that's it. Now this is your V out. Okay, now I told you for inverting amplifier we are going to calculate the input impedance, impedance of inverting amplifier. Okay, inverting amplifier, I told you this voltage is 0 volt, so this also will be 0 volt. So if you are standing from here and looking into the circuit, okay, so what you are going to see, there is some current here, I in. So you are going to see something like this. This is your V in and this is your R in, and you are going to see something like this if you are seeing from here. And this point is 0 volt, so it is virtually ground. It's virtual ground anyway, virtual ground. So what you are going to see from here, and this is your current I in. So you are just seeing only the resistance R in. So Z in non-inverting amplifier, inverting amplifier is nothing but just R in. There is no other resistance it will see because it is seeing a ground. So Z in will be equal to R in. Similarly, for the output impedance, there is no issue. It like previous expression, output impedance. If you want the proof, you can see it in the textbook Floyd in the appendix part. Okay, it's big steps are there for finding the output impedance. So for the output impedance, you will get Z out for the inverting amplifier. The output impedance is Z out divided by 1 plus, this is in the open loop, okay, open loop, 1 plus AOL into B. It's same like the previous. Okay, so that is very easy, you don't need to remember it. Okay, okay, we will see one problem. So problem, so find Z in closed loop and Z out in closed loop for the following amplifier. You can see here that this is minus, this is plus, and this is your Ri, and this is RF, and this is grounded. So what kind of amplifier this is? This is a, sorry, this V in. Okay, so what, this is an inverting amplifier basically, inverting amplifier. So you want to find the input and the output impedance, and it is given that AOL is equal to 50,000, then Z in is equal to 4 mega ohms, and Z out is equal to 50 ohms. Okay, now we will see what it is, how to find. So we will find the input impedance. So this is the answers. input impedance in closed loop. Okay, in closed loop, that is nothing but Z in inverting amplifier is equal to 1 plus, no, there is no 1 plus, it is nothing but Ri. Okay, and it has been given that Ri is equal to, I will write it, this is equal to 1 kilo ohm and this is given as 100 kilo ohm. So we will get the answer, this is equal to 1 kilo ohm. That's it. And the output impedance in closed loop is equal to Z out in inverting amplifier, which is equal to Z out divided by 1 plus AOL into B. So this B is Ri divided by Rf plus Ri. This is equal to 1 kilo divided by 100 kilo plus 100 kilo ohm plus 1 kilo ohm. So this is equal to 0.001 approximately anyway. Okay. Ri is 10 or 100. Let me check. It is yeah, it's 1 by 100. Okay, that's fine. So 1 by 101 actually. I think there is any issue with this calculation. Okay, I will use the exact number, that's better. Okay, I will use the exact number, that will be good. So 1 divided by 101. Okay, so it will be, okay, approximately it will be equal to 1 divided by 101, which is equal to 0.0099. So if you substitute this, Z out will be, Z out was 50 ohms divided by 1 plus, this is 50,000, and beta is 0. B is equal to 0.0099. Okay, so you will get it as 980 milli ohm. So I hope this is clear to you. Next, you can find the closed loop gain also. You can also find the closed loop gain. What is this closed loop gain? And what is this 2 we have already found out. Now what is the closed loop gain? So the closed loop gain is equal to minus Rf by Ri, which is equal to minus of 100 kilo ohm divided by 1 kilo ohm, which is equal to minus 100. That's it. You see there is a minus sign. That means that the polarity of the output will be changed. So I will give you 2 homework problems. So these are the 2 problems. You can practice it out. Okay, this is homework to you. Okay, I hope everything is clear. If you have any doubt, you can ask me through the course message. I will reply. Okay, thank you.